Hello and welcome to a new video on the Crypto2 YouTube channel. This video is the second part of the Steganography videos. If you haven't seen the first video, I highly recommend that you have a look at these, since in the first video I introduced the basic terms of steganography and I showed text steganography and how it works in Crypto2. In this video I want to show you image steganography and how to do it in Crypto2. Image steganography hides messages in digital images. And in Crypto2 we have two different methods to perform image steganography. The least significant bit or LSB method and the Bit Plane Complexity Segmentation or BPCS method. Both methods use a secret message and both messages use cover or carrier digital images. And they combine the secret message, or they hide the secret message, in this cover or carrier digital message to create a final digital image. And you could send this digital image to the receiver, and then the receiver can extract the secret message out of this digital image. In the following, I want to show you both methods in detail. Before I start showing you both methods, I want to give you an introduction to digital images. And a digital image has different color channels, a width W and a height H. And for example, a 24-bit image has three color channels, a red channel R, a green channel G, and a blue channel blue. And this is an RGB image. And each pixel of this image consists of 3 bytes and 1 byte per color channel. The total size of a 24-bit image is H multiplied the width multiplied 3 for each channel. And then you get the size in bytes. And of course, we have here no header information. The image files need this header information, for instance, to know what width and height we have. But for the computation, we omit the header information. And here's an example image file, or only the pixels of an example image file. And the pixels are just stored in an array of RGB values. So when you edit the file, for instance with a hex editor, you see 1 byte for the red channel, 1 byte for the green channel, and 1 byte for the blue channel. And then you get this pixel information. Then you go to the next one, and so on, and so on, and so on. And you have a huge array of RGB values. And to display this image on your screen, your computer needs the header information that tells you the width and the height. And then it first goes the width, time, and reads the pixels. And after width times these pixels, he goes to the next line and does the same for the next line, and the next line, and so on. Now let's have a look at the least significant bit or LSB method. And from now on, let's write the byte of each channel as an 8-bit vector. So you have the R channel here, which has bit R0 to R7, 8 bits. You have the green channel, which has bits green 0 to green 7. And you have the blue channel from bit or blue 0 to blue 7. And the least significant bit is the 0 bit. So this bit here in the red channel, this bit in the green channel, and this bit in the blue channel. And the least significant bit has the least significance on the value of a byte. And this is why we call this the least significant bit. And that means that a change makes nearly no difference in the color of the pixel, because the least significant bit here makes only a difference of 1. And here's an example of all 3 color channels and what happens when we change a bit of the channel. We have the red value here, for instance, 255 red, the green value 255, and the blue value 255. Now let's change the least significant bit, and you can see nearly, or you can't see, I assume, any difference between these 2 red values, these 2 green values, and these 2 blue values. And I changed all the different bits to see the difference between the color values. And starting from here, I can see on my screen a small difference in the red value here. With green, I can only see a difference here on my screen, but this may depend on the screen that I use or the screen you use to watch this video. And same applies to the blue channel here. I can see a difference only here in the change of the 0, 1, 2, 3, 4, 5th bit here. And from this on and this on here, you can also see a change in the blue value. And the LSB method uses the last significant bit, or maybe also more bits, of each channel to hide data. Let's assume we only use the 0 bit, the least significant bit. Then we have the red channel here with a change in this bit for our hidden data. Then the green channel here with a change in this bit of the data, also the least significant bit of the green channel, and the same in the blue channel. And we do this for all the pixels to hide our data. We take the first pixel, change the 3 values, the second pixel, change 3 values, and so on and so on and so on. And we would see no difference at all in the images. Here I have now an example of a picture where I changed all the bits. For instance, in this image here, I did not change anything. In the second image here, I changed only the first bit, so the least significant bit of the channel. So you see no difference. Or at least I can see no difference, but I assume you also see no difference. Here I changed the first 2 bits of each channel, then the first 3 bits, and the first 4 bits. And with the first 4 bits, it starts, at least to me on my screen, that I can see some changes in the image. And I go on. I changed the first 5 bits of each channel. And I did this for each of the pixels of the image. I changed the bits, so bit 0 to bit 4 here, with random values. I just took randomly generated data and put this in, but this also would work when you use, for instance, a text or an image values to change these values here. Then I changed for the next example here the first 6 bits of each channel, and you can see here huge difference compared to the original image. For instance, we have here false colors, the image gets grainy, and you can see that this is a very bad version of the image. Here we have a change of 7 bits of each channel, and you can nearly see what this image is here. You can see this is a flower, but it's very noisy right now. And of course, when we change all bits of all channels, then we just get noise or colorful noise here, and the image is completely destroyed. Now let's have a look at the Bit Plane Complexity Segmentation, or BPCS method. And the BPCS method works similar to the LSB method, and it hides data in the bits of the RGB channels. But it uses a, you can say, more clever method to do so. Because instead of using the same bits in each pixel, for instance using all the least significant bits or the 2 least significant bits and so on, this method uses more bits of pixels which are part of high complex regions of your image and less bits of pixels in low complex regions. And here I have an example. I have this nice picture of the ocean, and you can see here the sky, here's the ocean, and this here could be or is the coastline. And this here is an example for a low complexity region. So you have the sky here and it's nearly only one color, and you have a high complexity region, and this is where you have this water here, which is very complex. You see different color values, so you could hide more data in this region as in this region here, and this is what the BPCS method would do. It does this for each bit plane of the image and for each color channel individually. So it would look here, for instance, at the blue color channel and see that the blue color channel is more complex than, for instance, the red color channel, and would hide more data in the blue color channel than in the red data channel. And here it would look at all the color channels and would see here I can nearly hide no data at all. And what is a bit plane? A bit plane consists of all bits with the same index of a channel. For instance, the bit plane of channel red with index 0 are all least significant bits of this red channel. And the bit plane with index 1 would be all 1 bits of the red channel. The bit plane 2 would be all third bits, and so on. And for details on the BPCS method, you could also have a look at the corresponding Wikipedia article, BPCS steganography. Here's now an example for bit planes, and I show you all bit planes of the flower image that I used as example before. And here you see the bit plane of the red channel with index 0, so all least significant bits. Here you have the bit plane of all 1 bits, the bit plane of all 2 bits, the bit plane of 3 bits, and so on. And you can see that the bit plane 0 looks like noise, so it's highly complex, so you could hide a lot of data in this here because it wouldn't change anything at all. But when you look at, for instance, the last bit here, is a bit plane 7, where you see huge regions with the same color, when you change here something, it would change the image, and you could see this in the image. So in this example, we would take a lot of bits from these bit planes here, and starting with this bit plane here, where these get less complex, the algorithm would take less bits to hide data. Now I have a discussion and a comparison between the LSB and the BPCS methods. And with the LSB method, you can use up to 3 bits, which is about 37.5, or it's exactly 37.5% of each channel. That's bit 0, 1, and bit 2. And beginning with 4 bits, you could see many obvious differences compared to the original image. So we can use 3 bits of each channel with the LSB method, and we would not see many changes. And in contrast to that, or in comparison to that, the BPCS method allows the usage of about 42% of all bits of the same image. And we tested this with CT2. The CT2 implementation of BPCS tells you how many bits, or what is the percentage of bits you can use to hide data in your images. And the Crypto2 method gave us 42%. So this rate is higher than, of course, a rate of LSB. And the BPCS method hides this data in the image, and you would not see anything or nearly anything. So what is the hiding capacity of these two methods? The flower image has an uncompressed size of about 801 kilobyte as a bitmap file. A bitmap file is an uncompressed file that you can say contains the raw pixel data. And that means we can hide about 300 kilobyte of data using the LSB method, and we could hide about 336 kilobyte using the BPCS method. And probably these 336 kilobyte that we hide with BPCS, you could not see much, or you may also see nothing that was changed in the image, but maybe with the 300 kilobyte that we hide with the LSB method, you could see something in the image that has been changed. And now if you store the image in a JPEG format, the same image that we used, it has only a size of about 59 kilobyte. But the problem here would be that the JPEG algorithm to store this is not lossless. That means that your secret message would be destroyed using JPEG. So when you want to use image steganography in Crypto2 or image steganography in general, you should use a format that has a lossless compression. An example for this would be the PNG file format. Now, after we understand what image steganography is, and we had a look at the least significant bit method and the BPCS method, let's have a look at the new image steganography components that we have implemented recently in Crypto2. I'm here now in Crypto2 and I want to show you our implemented image steganography methods. And to find these, you go to the template section in the Start Center and you search for steganography. And then you have two entries here. We have image steganography with BPCS and we have image steganography with LSB. And I start with the LSB method by double-clicking on the template. And then we get the template. And we have here a text input, our secret message. This is hi, this is a secret message. Then we have our cover image, which is the same image that I used in the slides. Then we have the image steganography component here that has some different methods that we will see in a minute. Then we will see the stego image here. We will see the LSB extracted message also here. So this message will be the same as the secret message. And we have two modes, you can say. You click on the image steganography component, go to the settings, and it's not exactly modes, you can show the presentation or you can't show the presentation. When you unclick this here, then you can choose the bit masks that will be used for hiding the image. So this bit mask tells you that for the red channel, please only use the least significant bit. But we could also use the second bit, or we could use both bits. And of course, you could use all the bits. And I use this component here to generate the example picture that I have previously shown to you in the slides. But I will keep it to the first bit here, and then I will just click on play. And it takes a second. And then you get here the Stego image. And in this image, we have hidden the text, "Hi, this is a secret message," in the least significant bits of the red, green, and blue channel. Now let's have a look at the component, and we enable the presentation again. So we have to open it again a little, see more. And I click on play. And in this case, you won't see the image right away. We have to go here to this green marked button, or click on this button. And then you have this nice presentation where you can select bits you want to use. For instance, we could use the first two bits of the red channel, the bit 0 and bit 1, the same for the green and the same for the blue. And when you click on Apply Changes, it takes a second. And then it hides the image also in the Stego image. And the nice thing with the implemented algorithm in Crypto2 is that it not only hides this message, but it also hides the information which bits are used. So you have a very small header in front of your message that tells the receiver how to extract the rest of the message. Let's go back to the main menu. And then we have here some explanations that I won't go into detail, but you can click yourself through this nicely made component and then learn more about the LSB method. And you can see, for instance, here the pixel conversion. So we have here our red value, our green value, and our blue value for the pixel with the coordinates 0, 0. So with the pixel in this corner here, the first pixel of our picture. And we can see the bits before we have hidden the message. So we have 0, 0 for red, and we have 0, 0 for red. Then we have 1, 1 for green, but 1, 0 for green after we have hidden our message. And for blue we have 0, 0 and 0, 0 again. And with this button here, you can step through the pixels, so it will increment the X value. And you can compare all the pixel values. You see the difference in the channels here, and you see the different color value here. Now let's go back to the main menu, choose bits, and let's choose all the bits. So this template here and this component is really nice to play around with image steganography. Now let's apply the changes. And I don't know if you can see this, maybe not on YouTube. We have here very few pixels that are totally wrong now because we used all of the bits of the color channels. But to get it a little more detailed, we can have a look at the pixel conversion here. And we start again with 0, 0 pixel. So this is the pixel value before we have hidden the image, the message. And this is the pixel value or the color after we have hidden the message. And as you can see, we use all the bits, so it changes all the bits according to our secret message. And it uses the ASCII encoding of these letters here to hide these in the pixels. Now let's go through the pixels. And as you can see, some of the values have totally been changed. So this was green, now it's purple. And at some point we will see that the pixels will have the same value, and this is of course because we reached the end of our message. Let's go back to the main menu, and here we have the last thing I want to show. We have overview and hiding capacity of the image, and this is really nice. It tells you some meta information. For instance, we have here the message length. This is 232 bit, so this is not very a large message clearly. Then we have the image width and image height, 640 by 427 pixels. We have the numbers of bits chosen to hide the secret message, 24, which are all our channels. And here's the hiding capacity. And since we have selected all the bits here, the hiding capacity in percentage is 100%. Now let's go to the BPCS method. So I go back to the Start Center and I open the image steganography with BPCS template. And I will just start this here right now. This takes a little more time to be computed. And we see here it's the same. We have this is a hi, this is a secret message. Hi, this is a secret message. And we have our picture here. What you could do right now here is also to click on the understand how the algorithm works. And it gives you a nice explanation of the BPCS algorithm and different examples, how this works with the complex regions and so on. But that you can explore by yourself. Then we have C hiding process. And this gets more interesting because this works not only on pixel level, it works on block level. So it takes some blocks of your image and it computes the complexity. And then it tells you how it changes these blocks. And you can step through these blocks and then you see the different complexity regions or the complexity of the different blocks and how it changes these according to your message. And then you have also some meta information here. For instance, you have total number of image blocks in this image. So we have 100,488 blocks in this image. And the number of complex blocks or complex image blocks that we can use for hiding our message is 42,201. And the hiding capacity is 2,685 kilobits. And that's the hiding capacity I already have shown you in the slides. It's about 42%. So it's higher than what we have chosen with the 3 bits or what we have achieved with the 3 bits of each channel in the LSB. Let's go back to the main menu. And now what's also interesting here is we can have a look at the pixel conversion again. So we can have a look at the different pixels. And as you can see, many pixels look the same because the algorithm is so clever to select the pixels according to this complex region calculation. Now let's go back to the main menu and let's have a look at the final nice presentation part here. That's the C different bit planes. I will increase the size. I hope that you can see this on YouTube. I don't know what the YouTube algorithm will make out of these. So we have here the bit plane 0, bit plane 1, 2, 3. So these are all bits of the image that are the 0 bits of the red channel here. You can change the channel. Here you can click on the green bit planes and the blue bit planes. But let's keep the red bit planes. And it marks all the pixels with red color that have this bit set to 1 and all bits with white color that are set to 0. And as you can see here, the different bit planes have different complexities. So the least significant bit has the highest complexity, so this can be used by our algorithm to hide data. And the higher the number of the bit gets, the less the complexity is. And here you can see why you can't hide anything in the bit plane 7, bit plane 6. You would destroy important parts of the image and one could see that there's something wrong with the image or something hidden in the image. And now we close this again. And with the BPCS method, it's the same as with the LSB method. It puts in front of the hidden blocks. No, I don't think it does this. The BPCS method computes the bits that it can use for hiding based on the image information. So I assume, I'm not 100% sure. To be sure, I would have to read the bachelor thesis again of the student who implemented this. The BPCS method computes the bits it can use for hiding, and it does the same for its extraction. So when you hide a message and use BPCS, you have no header in front of the message. But I'm not 100% sure, but I think it is this way. And with the extraction, it computes the same and extracts the message. And yes, now we reached nearly the end of this video. So this was everything that I wanted to show you with image steganography and what we have implemented in Crypto2. So you could now go to Crypto2 and try these on your own. To use these methods, you have to download the nightly build, but clearly these methods will be also available in the next release version of Crypto2. I hope you enjoyed this video. If yes, please give a thumbs up. It really helps me to grow the channel to make Crypto2 more popular. If you don't like the video, you know what to do. Give a thumbs down. And if you did not yet subscribe to our channel, I would be really happy if you do so. This also helps much. And yeah, this was everything I wanted to show you in this short video. Thank you very much for watching and see you in the next video.